Husain College and the principal of college and the head of the Department of Mathematics and faculty members, especially my friend Dr. Zakir for inviting me to this webinar. Thank you all once again. Today's topic is basic concepts of modern algebra. So I am going to start with group theory. Okay. If anybody wants to interact with me, you can interact with me. Please unmute your catechs. Then you can interact with me. Okay. If you have any doubt at all. Group theory. The board is visible, sir? Yes, the board is visible.
Yes, sir, visible, sir.
Okay, okay, fine. Let us take a non-empty set. Let us take a non-empty set G. Okay. Now I am going to define an operation, binary operation. Binary operation is a function from G cross G into G. G cross into G. G cross G into G. So that is nothing but, so A comma B means A star B. Star may be usual addition or multiplication or some other operations. Whatever we define, we will take it star. Usually we will take the operation star as either plus or dot, multiplication, addition and multiplication. Okay. Now, what does it mean? What is the function? What is the meaning of function? For each element in G cross G, there exists a unique element in G. There exists a unique image in G. That means if you take A comma B, there will be one element A star B. That means if you take one element from G cross G is nothing but taking two elements in G. That means for any two element, A comma B belongs to G, A comma B belongs to G, then A star B is also belongs to G. So therefore, if you take any two elements, for every A comma B belongs to G, then A star B belongs to G, that operation is called closure operation, closure property. With respect to star, star may be addition or multiplication. Okay. So therefore, instead of saying the closure property, I am saying that star is a function from G cross G into G. That's all. Both the things are same. So after saying that, no need to say that star satisfies closure property. Both the things are same. So therefore, first one is this function. The second property is associativity property. Associative property is saying that A star B star C, which is equal to A star B star C, for all A, B, C belongs to G. Number 3 is there exists 0 belongs to G. There exists 0 belongs to G such that 0 star A, which is equal to A star 0. So let us take, suppose if it is plus, I can take 0. In general, I can take E. E may be 0 if it is addition. That E may be 1 if it is multiplication. Okay, so let us take in general So therefore, E star A is equal to A star E, which is equal to again A. So that means there exists only one element belongs to G. That element satisfies these conditions. Okay. So this is called existence of identity. So we have to see that, we have to find that whether the identities exist or not. Number 4 is number 1 associative, number 2, number 4 is for each A in G, for each A in G, there exists A dash in G, there exists A dash in G such that A star A dash, which is equal to A dash star A, which is equal to identity, which is equal to identity. Okay. So therefore, closure, associativity, existence of identity, then inverse. So if the set satisfies these 4 conditions, then this set is called a group. The set is called a group. In addition, suppose A star B is equal to B star A for all A comma B belongs to G, then the group becomes abelian group. The group becomes abelian group. Okay, so the most important thing is we have to find the existence of identity, inverse for each element, then closure property. Associative will satisfy almost in all sets over the real numbers. Okay. Then example of a groups. First of all, we have the number system. Natural number is a subset of integer. Integer is a subset of Q. Q is a subset of R. R is a subset of C. This is our number system. So let us take natural number. Let us take natural number. With the operation, let us take either plus or dot. Either plus or dot. Suppose if you take plus. The first property is closure property. You have to check. If you take any 2 element, if you add it, again that addition again belongs to this n, then plus satisfies closure property. So definitely the natural number consists of 1, 2, 3, etc. If you take any 2 element, if you add it, again that element belongs to the natural number. Therefore, closure property satisfies. Associativity also definitely will satisfy. Already I said, any set over the real number, automatically associativity will be satisfied. No need to check. The third thing is existence of identity. With respect to plus, we have to check whether 0 is there or not. Here 0 is not there, therefore identity is not there. Okay, then identity is not there. Inverse in the sense, if you take any element plus some other element which is equal to identity becomes 0. If 2 plus something which is equal to 0 means you will be getting -2 here, but -2 is not there. So therefore we can say that inverse is also not satisfied. Okay, so therefore this set is not a group, and also we can say that suppose these 2 conditions are satisfied, the set n is called semi-group. We can say that it is a semi-group. Okay. So similarly, we start with the natural number. The natural number is not a group. Natural number is a semi-group with respect to plus. With respect to multiplication, closure property is there. The same kind of check. If you take any two element, multiply it, definitely again it will be there. Number two is associativity, sure. Number three is also is there. So number three is the multiplicative identity. Multiplicative identity is always 1. Additive identity is 0. So therefore, the third condition also satisfies. So fourth one is, suppose if you take the element 1, so 1 has inverse. 1 into 1 is equal to identity. So therefore 1 has inverse. But 2 into 1 by 2 will become a 1. So therefore 1 by 2 is not there in this side. So therefore except 1, no element of natural number has a inverse. So therefore inverse is not satisfied. So therefore, so this group, the natural number with respect to multiplication is not a group, but it satisfies three conditions. So we can say that this is called monoid. This is called monoid. First two conditions is semi-group. First three conditions we can say that it is monoid. Fourth one also satisfies. Then it is a group with group. Okay. Then you come to the integers. Integers is nothing but 0 plus or minus 1 plus or minus 2 etc. This is integer. Now you see that first you can take the plus operation, addition. So you can check very well that if you take any two element, add it, again it will be there. Therefore it is closed with respect to addition. Number two, associativity is there. Number three, additive identity, 0 is also there. Number four, for each element, suppose you take 2 plus the identity, that is inverse minus 2 is equal to 0. So therefore A star A dash is equal to identity. That means what? Here star becomes plus. Additive identity is 0. So therefore if you take 2 plus the A dash, definitely minus 2 will be minus 2, then only it will become 0. So there exists A dash minus 2 is also is there. Okay, also belong to that. Therefore it is called the inverse of 2 is minus 2. Additive inverse of 2 is minus 2. The additive inverse of minus 2 is plus 2. So therefore every element has its has inverse. Therefore inverse is also satisfied. Therefore in our number system, the smallest group in our number system, therefore z comma plus is a group, and it also satisfies a star a plus b is equal to b plus a. Therefore this is an abelian group with respect to plus addition, z plus. So now I am coming to z plus is the very interesting group. Okay, with respect to addition is a group, abelian group. Then I am coming to the multiplication operation. Okay, now the same thing, if you take any two element, multiply it, okay. Associativity is also okay. 1 is there because multiplicative identity is 1. 1 is also is there. Then you have to check the inverse. A dot A dash is equal to 1 because dot star becomes dot. Then E becomes 1 because of multiplicative operation. So therefore, suppose I am taking 1, definitely I have the multiplicative inverse. Therefore, 1 have inverse. minus 1 also have inverse, multiplicative inverse, but 2 doesn't have inverse 1 by 2, then it will become 1 by 2 will not be in this z. So therefore, except 1 and minus 1, except 1 and minus 1, except 1 and minus 1, so no element has inverse, multiplicative inverse. Therefore, z comma dot is not a group. Z comma dot is not a group, but it is a monoid. But it is a monoid. But it is a monoid. Okay. Then I am coming to the next number system, that is Q. Okay. So therefore here Q, the set of all rational numbers with respect to plus I am taking. So Q is nothing but the set of all P by Q such that P belongs to Z and Q belongs to N. The set of all rational number is of the form P by Q. So this is called rational numbers. Rational number. So here definitely Z comma plus is an abelian group. I can say that easily. I can say that Q comma plus is an abelian group. Abelian group. Okay. No need to check because identity is there, inverse is there, additive inverse is there. Because it is in Z, automatically will be in Q. Okay. So therefore, it's an abelian group. Then come to Q comma dot. Q comma dot. Here, everything is there, but 0 only doesn't have the inverse. 0 only doesn't have the inverse. Multiplicative inverse. Otherwise, 2, the inverse of 2 is 1 by 2, the inverse of 1 by 2 is 2. Whatever you take the rational number, definitely the inverse is also, multiplicative inverse also will be there. So therefore, 1 is also will be there, 1 is also a rational number. Identity is there, closure property is there, but multiplicative identity except 0, every element of this Q have inverse. So therefore, I can write here Q star. Q star in the sense, let us take the rational number minus 0. So except 0, this is a multiplicative group. This is a multiplicative group. So therefore, the Q star is also a group. So therefore, then the same kind of discussion, argument, R is also a, or star with respect to addition is also a abelian group. This is also a abelian group with respect to addition, with respect to multiplication. Complex number is also complex number. Here, see, the complex number is of the form A plus IB such that A and B belongs to R. This is nothing but the set of all complex numbers. Otherwise, we can say that this is a complex plane. Otherwise, we can say that this is a complex plane. Okay. Here, the same thing. Here, 0 is there. 0 is additive. Identity 0 plus 0i. Additive identity. Closure property is also there. So therefore, C comma plus is an abelian group. Dot. With respect to dot, 1 plus 0i is also there. So this is the multiplicative identity. This is also a multiplicative identity. Then inverse. Suppose let us take A plus IB. What will be the inverse? What will be the inverse? If you multiply it, A minus IB divided by A square plus B square, which is equal to 1. Which is equal to 1. Okay. So therefore, the inverse of A plus IB is equal to A minus IB divided by A square plus you multiply these two elements, you will be getting 1. So therefore the inverse of a plus ib is equal to a minus ib by a square plus b square. So therefore these are all the groups in our number system. Suppose I am asking that, suppose let us take g is equal to -3, -2, 1, -1, 0, 1, 2, 3. Can we say that this g with respect to plus a group? Okay. So here identity is there, 0 is identity. Then associativity also will satisfy. Then inverse also is there. The inverse of 1 is -1, inverse of 2 is -2. So associativity, existence of identity, then inverse of each element, everything is there. But you have to check the closure property. But here the closure property fails. So therefore 2, 3 belongs to G. 2 plus 3 equal to 5. 2 plus 3 is equal to 5, which does not belong to this set G. So therefore this is not a group. With respect to addition. Then the cube root of unity. Cube roots of unity. The cube roots of unity. A set consisting of cube root of unity in the sense cube root 1 power 1 by 3 cube root of unity 1. Cube root of 1 is nothing but cube root of unity. Let us take this is x. So therefore 1 is equal to x cube. So therefore x cube minus 1 is equal to 0. So the how many solutions are there? X cube minus 1 is equal to 0. That solutions are the roots of cube root of unity. So we can find in many ways. Therefore otherwise we can say that x cube is equal to 1. 1 can be written as cos 2n pi plus I sin 2n pi or something like that. Okay. So therefore here we can say that, so this is 1 minus 1 by 2 plus root 3 by 2 I and minus 1 by 2 minus root 3 by 2. So therefore the set consisting of the cube roots are the cube roots of unity. So therefore roots, there are 3 roots. Let us take this is equal to W1, this is equal to W2, this is equal to W3. This is most important. If you know how to construct this set, immediately you can construct the 6th roots of unity. 6th root of unity. There will be a 6 roots. For that equation x power 6 minus 1. Then you can have a multiplication table for that. So therefore now I am giving you a multiplication table. W1, W2, W3. So therefore W1, W2, W3. Okay. W1 into W1 is equal. W1 into W1 is equal to, what will you get? W1 into W1. So therefore W1 is equal to minus 1 by 2 plus root 3 by 2 the whole square. Therefore 1 by 4 minus 2 root 3 by 4 minus 2ab 4 plus 3 by 4. Therefore we can write Therefore, we can write 3 by 4 plus 1 by 4. So this is a square. This is 3 by 4. 3 by 4. This is 2 times of minus 2 times of 3 by 4. Okay. So therefore 1 minus 2 root 3 by 4 or otherwise root 3 by 2. 1 minus root 3 by 2 I. Okay. So let us take I here. So therefore this is I. Therefore 1 minus, that is 1 by 2 root 3 by 2. So therefore
Excuse me, Professor. Alapum, Professor.
yes,
Professor.
yes.
Professor.
சொல்லுங்க Professor.
The blackboard is not clear in the set box command, Professor.
அப்படியா?
ஆமா Professor.
Not clear?
பிக் லெட்டர் கொஞ்சம் பெரிய லெட்டர்ஸா கொஞ்சம் பேஸ் பண்ணிக்கிங்க.
சரி, ரைட்.
கிளியர்.
ரைட்.
இந்த செட் பாக்ஸ் கமாண்ட்
அப்படியா? சரி. it is not visible.
இது பிளாக் போர்ட் இஸ் நாட் கிளியர்.
சரி, ஓகே.
Thank you Professor. Thank you.
Okay. You see that? Okay, I will try to write to the big size, okay? Okay, so therefore I can write W1 into W2 is equal to W2. Okay, if you multiply W1 into W1, again you will be getting W2. Again W3, W1, W3, W1, W2. So therefore W3 is identity element, therefore W1, W2, W3. If you multiply it, you will be getting it. Okay. So this is the multiplication table for this group. Okay. So therefore I am considering this a set, non-empty set with a multiplication operation. Okay. So see that W1 into W2 is again W2. So therefore all products again it is belongs to that. So therefore this group is closure. This non-empty set, this set is closed under dot. Closed under dot. Okay. Then see that associativity also is there. Then one identity is there, existence of identity, that is one. Then inverse. The inverse of W1 is equal to W2 because W1 into W2 is equal to W3 is equal to 1. So therefore inverse of W1 is equal to W2, inverse of W2 is equal to W1. So likewise we can check each and every element of this set have the inverse. That's the inverse. Each element has inverse. So therefore all elements have their inverse. So therefore this set is a group with respect to multiplication. Okay. So this is an important example of the group theory. If I multiply it one by one, it will take time. So that's why I have written that. Next set is, let us consider another example. This is most important example. So this is 1 comma minus 1 comma I comma minus I. This is a set. This is a subset of where? This is a subset of complex numbers. I am taking the set with the operation, multiplication operation I am taking. So this is the group, is an abelian group. Here also you can make a multiplication table, scalar table also you can make it. The same thing. The identity element is 1. Closure properties also satisfies. Closure property also satisfies. Identity is 1. Associative is there. The inverse of 1 is 1. The inverse of -1 is also -1. The inverse of I is equal to, will be getting 1. What will be the inverse? Inverse of I is equal to -I. Okay, inverse of I is equal to -I, inverse of -I is equal to I. Okay, so therefore this is also the most important group, the finite group with respect to multiplication. The finite group with respect to multiplication. Then there are many properties. There are many properties in group theory. I am going to give 2-3 properties only. Number 1 is A inverse of inverse is equal to A. Number 2 is AB the whole inverse equal to B inverse A inverse. Professor, now is it visible? Husain, professor?
Visible, sir. Visible, sir.
Yes, professor.
Sir, visible, sir, visible.
Okay. The third one is the equation AX plus B. AX is equal to B has unique solution. Has a unique solution. The most important properties, the three for all A comma B belongs to G. Okay. Now the proof is very interesting. So let A belongs to G. So this is true for every A belongs to G. This is true for every AB belongs to G. Let A belongs to G. G is a proof. Therefore, A inverse also belongs to G. A inverse also belongs to G. So therefore, inverse of A inverse also belongs to G. Because if you take any element belongs to G, there exists the inverse. So therefore, A inverse, okay, of inverse also belongs to G. By the closure property, A inverse belongs to G. If you take any element, the inverse of that element also belongs to G because of group. So therefore, A inverse, by using the closure property, the whole inverse again belongs to G. And also A dash equal to identity. So therefore, A inverse of the whole inverse is equal to identity. Now we can multiply it by A on both sides. We can multiply it by A on both sides. Therefore, A inverse. Therefore, A inverse the whole inverse is equal to A times of E. By using associativity, A inverse of inverse is equal to A is equal to again A. So therefore, this is E times of A inverse of inverse is equal to A. So therefore again A inverse of inverse is equal to A. You have to write all those steps, then only you will be getting A inverse of inverse is equal to A. So each and every step has a meaning. Okay. So therefore, this is most important property that A inverse of inverse is equal to A. So here, the second property is AB into B inverse A inverse is equal to, by using associativity, A times of B inverse of A inverse, which is equal to A E times of A inverse. Therefore, A inverse. So this is equal to E. Okay. Similarly, B inverse A inverse into AB is equal to B inverse, by again associativity, A inverse A is equal to E. Then B, therefore again it is equal to E. I can write. So therefore, A into A dash equal to E, or A into some element is equal to E. Therefore, this is the inverse of this, or this is the inverse of this. So therefore, the inverse of AB, the inverse of AB is equal to B inverse A inverse. Otherwise, I can say that the inverse of AB is equal to B inverse A inverse. So therefore, this property is also most important. Number three is for any element A comma B belongs to G, the equation AX is equal to B has a unique solution. Okay. So here, what will be the solution? Suppose AX is equal to B, multiplying it by A inverse on both sides. Again, you will be getting E times of X. Therefore, X is equal to A inverse B is a solution. It's a solution of the equation AX is equal to B. So now we have the solution. But I am going to prove that this is a unique solution. This will be a unique solution. Suppose this equation has two solutions. Suppose let x1 and x2 be two solutions. That means what? Ax is equal to b. X1 is a solution, means Ax1 is equal to b, and Ax2 is also equal to b. Now I am going to prove that x1 is equal to x2. What is x1? X1 is equal to what? X1 is equal to A inverse B. X1 is equal to A inverse B. Again I can write A inverse of what is B? Again it is Ax2. Okay. Now this is equal to A inverse of A into x2. Therefore E times of x. Therefore Ax2. Therefore this is x2. Therefore this is x2. So therefore x1 is equal to x2. Similarly, I can prove that YA is equal to B. This equation also has the unique solution. So these three properties are most important in the group theory. Okay, then now we know that what is group, what is the example of group, then the number system. So we have seen one by one. Now, what is order of the group? What is the order of the group? Okay. So let G be a group, a non-empty set. The number of elements in the group is called order. Okay. So the order of Z is equal to infinity. So therefore, the Z has infinite order. Because of Z comma plus is a group, but the number of elements is infinite. So therefore, this is the Z has an infinite order. Number one. Next is, what about Q is also, the order of Q is infinite, etc. Then what about cube root of unity? Order of that set is equal to only 3 elements, order of 3. So then 1 minus 1, I minus I, The order of this group is equal to 4. Very simple. But number of elements in the group is called order of the group. Okay. Then order of an element, that is most important. Order of an element. Okay. Let G be a group. Let G be a group. If, and let A belongs to G, and let A belongs to G, if there exists a positive integer, there exists a least positive integer, such that A power n is equal to E. A power n is equal to E. A power n or A power m, whatever it may be. Then we can say that order of A is equal to n. Order of A is equal to n. So you should know the difference between order of a group, order of an element. What is the relation between them? So order of an element. Suppose let us take G is equal to 1, minus 1, I, minus I. Okay. So this is the multiplicative, this is group with multiplication. Group with the multiplication. So therefore, I can write, suppose what I am taking element 1 belongs to G, that is A. Okay. So there exists the least positive integer 1 power 1, that is A power 1 is equal to identity. Identity is 1. Then 1 power 2 is also 1. 1 power 3 is also 1. So therefore, there are many positive integers. Integers which satisfy A power n is equal to E. A power n is equal to E because A is equal to 1. E is also 1. Okay. So out of which I am going to choose the least positive integer. What will be the least positive integer? 1 is the least positive integer. So therefore, there exists a least positive integer m is equal to 1, such that A power m is equal to E. Therefore, 1 power 1 is equal to 1. So therefore, order of 1 is equal to 1. Okay, that is most important. Similarly, I can suppose let A is equal to minus 1. A is equal to minus 1. So therefore, minus 1 power, there exists a positive integers 2. This is equal to 1. Then minus 4 is equal to 1. So therefore, the integers 2 satisfies this condition. This 4 satisfies this condition. This 6 satisfies this condition. So therefore, there are many even integers satisfying this condition. So therefore, our definition is if there exists a least positive integer which satisfies this, therefore the least positive integer is 2. Therefore, the order of minus 1 is equal to 2. The order of minus 1 is equal to 2. Similarly, we can say that what about I? So I power 4. I squared is minus 1. I power 4 is equal to 1. Identity. Then I power 8 is equal to 1. Identity. So therefore, here there are many integers satisfying this condition. The least positive integer is 4. So therefore, order of I is equal to 4. Similarly, order of minus I is also equal to 4. Okay. So this is order of an element, that is most important. So this is the group with multiplication. What about integers? integers is a group with respect to plus is a group. Okay. What about order of an element? The same definition. A power n is equal to E. So here E is nothing but multiplication group. What we have taken E is 1. Here n times of A plus A into A. Therefore n times. So therefore I can write A power n. That is most important. If it is an additive group, A power n becomes, or the A power m becomes A plus, etc. A, how many times? M times, which is equal to 0. Identity is, here is 1, here is 0. That is most important. So m times of A. So therefore, m times of A is equal to 0. The same definition. The same, let A belongs to Z. Let A belongs to Z. The order of A is defined as, order of an element A is defined as, if there exists a least positive integer m such that MA is equal to 0. Both the definitions are same. If it is a group with addition, we have to check this. If it is a group with multiplication, we have to check A power m is equal to 1. Okay. So here, what about order? Is it consisting of 0, plus or minus 1, plus or minus 2, etc. Okay. 0, we can have order because 0 times 0 is equal to 0. 0 plus 0 is also equal to 0. So therefore 0 has order. Therefore the order of 0, definitely this is equal to 1. Okay. Now let us take 1. We can find any m such that MA is equal to 0. M times of 1 is equal to 0. Can you find any positive integer m which satisfies this condition? The answer is no. Okay. So therefore, here there is no such m, there is no such positive integer m which satisfies this condition. So therefore, 1 is of infinite order. Has no order. So therefore, except 0, no elements of Z has except 0, all the elements have infinite order. We can say like that. Except 0, all the elements of Z is of infinite order. Okay. Then next is similarly you can check it the cube root of unity and all. Okay. So cube root of unity W cube is equal to 1. W cube is equal to 1. For example, I am telling you. Because W1 into W1 is equal to W1 into W1 is equal to W like a multiplication table, you can see that. What about the W1 into W1? W1 into W1 is equal to W2. W1 into W1 is equal to W2. Again, W1 into W1 into, this is W1. W1 is equal to W2 into W1. This is equal to W3. That is 1. So therefore, W1 cube is equal to 1. W1 power 6 is equal to 1. Likewise, we can calculate. So therefore, order of W1 is equal to 3. This will be the least positive integer. You can check it. Okay. Then concept is subgroup. So far what we have seen that what is group, what is example, what are the example of a group, then order of a group or order of an element. Okay, then subgroup. Let G be a group, H be a subset of G, H be a subset of G, then non-empty subset. This non-empty subset is said to be a subgroup. Is said to be a subgroup. H is itself a subgroup. It's a group. So therefore, any subset which satisfies all the conditions of group, then we say that this H is a subgroup of G. Subgroup of G. And also, by proving some theorem and all, it is enough to say that H is a subgroup of G. H is a subgroup of G if and only if AB inverse belongs to H, or otherwise A inverse B also belongs to H. Both the things are same. So H is itself a group. Instead of saying all four conditions, it is enough to prove that AB inverse belongs to H. There is a theorem. Okay, so you should understand that. Then, what are the subgroups? Any group is a subgroup of itself. Any group is a subset of itself. Z is a subgroup of rational number with respect to addition. Q star is a subgroup of R star. R star is also a subgroup of C star. Okay. So therefore here N is not a subgroup of Z. Okay. So these are all some concepts. Then the next concept is I am moving into the cyclic group. Okay. This is most important concept. Let G be a group. Okay. Then when we say that this G is said to be a cyclic group, if for some A belongs to G, for every X belongs to G, then for every X belongs to G is of the form A power M, where M belongs to Z. That means every element of X of G can be written as A power M. That's all. A power M. Okay. M belongs to Z. This is the concept. Okay. So this group is called cyclic group. So every element is of the form A square, A cube, A power 4, A power 5, A power 6. So therefore all the elements will be generated by a single element A. Therefore this A is called generator of the cyclic group. generator of the cyclic group. Okay. Sir, each group has only one generator? No, not like that. Not necessary. More than one generator also will be there. Okay. So therefore, any element of G can be expressed as in the a power m form for each m belongs to integers. This is called cyclic group. Example of a cyclic group is, again I am taking the same group. This is equal to 1 minus 1 I minus I. This is the cyclic group. Here I am going to take the generator. Let A belongs to A is equal to I am taking. So I is the generator. I am going to construct all the elements from this particular element. I am going to construct all the elements from this particular element. So all in A power m form only. A power 1, that is I power 1, one element. Okay, I power 1 is I is there. Then I power 2, this is minus 1. I square is minus 1. I power 1, I power 2 is minus 1. I power 3 is equal to minus I. I power 4 is equal to 1. Identity. So therefore you will be getting I power 1, I power 2, I power 3 and I power 4, which is equal to E. Which is equal to E. This group is called cyclic group. I is the generator. I is the generator. Okay. Then what about another generator? Let us take A is equal to minus I. This is also a generator. This is also a generator. So therefore, minus I square. Minus I is minus I. Minus I square is equal to minus 1. Then minus I the whole cube. I square minus 1, that is plus I. Then I minus I power 4. Again, which is equal to 1, that is identity element. So therefore, this group has two generators, I and minus I. One is not a generator, minus 1 is not a generator of this group. Okay. So therefore, this is the cyclic group. Is there, you can see that, is there any relationship between order of the group and order of the generator? Okay. Order of the group is 4 here. What will be the order of the generator? Order of the generator is equal to what? There is the least positive integer, such that A power m is equal to E. So therefore here is order is 4. Here is also order is 4. So therefore you can find that is there any relation between the order of the generator and order of the group? Both will be same. Okay. So then what about the integers? What about the integers? Integer is a cyclic group. Is question. Integer is a group with respect to plus. A cyclic. Answer is yes. Yes. The generator is A is equal to 1. The generator is 1. Okay. So therefore here any element can be expressed as, so any element in multiplicative group, any x can be written as A power m. M belongs to Z. M belongs to Z, yes. Now I am saying that this is a group with respect to addition. The same definition again I can write x is equal to n. Now because it is multiplication a times a into m times, here is a plus m times. Both the things are same. So again the all z belongs to m. So one is a generator. One is a generator. So therefore, suppose x I am taking 5 from z. Okay, 5 can be written as 1 plus 1 plus 1 plus 1 plus 1 5 times. So therefore, so this is equal to 5 into 1. I can write x can be written as 5 into 1. Okay, so 0 times of 1 because m belongs to z, 0 belongs to z. Understood? So therefore, if you take any minus 5, if you take any minus 5 also can be written as m belongs to z minus 5 times of 1 ma minus 5 times of 1. So therefore minus 1, that is generator, minus 1 time minus 1 time plus, therefore it is minus 5 times of 1. Clear? So any x can be written as m times of a, m belongs to z. Z means what? Z means plus and minus also will be there. Okay. So therefore this group, so you have to find a difference a power n and ma. Ma for the group with addition, a power m is a group with multiplication. That is most important there. Okay. So therefore z comma plus is also a cyclic group. Okay. So therefore one is only the generator. Okay. So therefore next one is z power z8. This is integer modulo 8. This is integer modulo 8. So this is equal to 0, 1, 2, 3, 4, 5, 6, 7. Okay. So we can also say that this is congruence modulo 8. Congruence modulo 8. Suppose A is congruent to B mod 8. Suppose A is congruent to B mod 8. If and only if 8 divides A minus B. 8 divides A minus B. Okay. So here, this is a cyclic group. This is a cyclic group. Because Z power 8 is a group, first of all. It is a group. This is a group with respect to addition. It's a group with respect to addition. 0 is there. 1 is there. Okay. 0 is there. Identity exists. If you add 1 plus 2 is 3. 5 plus 6 is 11. 11 is nothing but 11 minus 8. 3. 11 is nothing but 3. Okay. So therefore, you can check very well that. Okay. When you divide this 11 by 8, the remainder will be the operation. Okay, the remainder will be the number. Okay, so therefore here z comma 8 is a group with respect to addition. Okay, now I am going to say that the generator, 1 is the generator. If you take any element, so therefore I can write that element 5 is equal to some m times of 1. M belongs to z. I can write. Okay, good. All the elements I can write. Similarly, suppose I am going to take 3. So 3 is an element. Suppose 3 plus 3 is equal to 6 is also an element. Therefore, 6 also can be written as 2 times of 3. Then 3 plus 3 plus 3, 9. 9 is equal to 1. 1 also can be written as in MA form. Okay, MA form. Then 3 plus 3 plus 3 plus 3. Okay, 12. So therefore again you will be getting 4. So therefore 4 is also can be written as 4 times of 3. So therefore then 3 plus 3 plus 3 plus 3 plus 3, 15. So this is equal to 7. When 15 is divided by 8, the remainder will be 7. That will be the rule. Okay. So therefore 1, 4, 3, 7. Likewise, you will be getting 18. 18 minus 8, you will be getting 10. Okay. So therefore, not 10. 18, 18 minus 12, that is 6, you will be getting 5, 6, 18. 18 minus 16. So therefore you will be getting 2. You will be getting 2. Okay. So therefore you will be getting 1, 2. Then 18, 15, 18, 21 minus 16. You will be getting 5. You will be getting 5. So 1, 2, 1, 2, 3, 1, 2, 3. 3 is equal to 3. 1, 2, 3, 4, 5, 6, 7. Okay, you will be getting all. So therefore 0 also you can write 0 times of 3. So therefore, this 3 generates all the elements of the group. Therefore this 3 is the generator. Now you come to A is equal to 2. Okay. So therefore 2 also can be written as 2, 1 times of 2. Okay. 2 plus 2 equal to 4. Okay. 2, 4 is okay. 2 plus 2 plus 2 is equal to 6. 2 plus 2 plus 2 plus 2 equal to 8. 8 is nothing but what? 0. Okay. So therefore again 10. 2 plus 2 plus 2. 5 times of 2 equal to 10. That is nothing but 2. 6 times of 2, 12, which is nothing but 4 again. 7 times of 2, 14. You will be getting again 6. So this 2 generates 0, 2, 4, 6, 0, 2, 4, 6, 0, 2, 4, 6. Therefore, this 2 definitely will not generate all the elements of z power 8, z8. So therefore, 2 is not a generator. Similarly, 4 is not a generator. 6 is not a generator. But 1, 3, 5, 7 are all generators. Okay. So therefore, the generator of this group is most important group. Okay, this is the cyclic group. Then sixth root of unity, if I go there, it will take time. The important group I am going to know that is permutation group. That is most important group. This is called the permutation group. Okay. Permutation in the sense, you consider a set X 1, 2, 3. Okay. I am taking a function f from x into x. Okay. So I can 1, 2, 3. Domain is 1, 2, 3. Codomain is also 1, 2, 3. Now I am going to find all the 1, 1 onto map. I am going to find all the 1, 1 onto map. Okay. I am going to collect it. I am going to collect it. So that is nothing but a set. The set consists of all p functions, all p such that this p is a function from x1 into x is 1, 1 and onto, or is bijection. The collection of all bijection from this set to this set. What are the possibilities? So 1 1 means this may be the one of the choice. Okay, so therefore I can write 1 2 3 again 1 2 3. So this is called a permutation. 1 goes to 1, again 2 goes to 2, again 3 goes to 2, 3. Therefore, this is called identity permutation. Therefore, let us take this is B. Okay. Or otherwise, I can take it is I. Okay. Now, next what are the chances? You can see that 1 goes to 2, 2 goes to 3, 3 goes to 1. So therefore, let us take 1, 2, 3. 1 goes to 2, 2, 3, 1. 2, 3, 1. This is, let us take, this is some function. Therefore, let us take sigma 1. Okay. Are you following? So therefore, you have to collect all 1, 1 onto functions from the set into the another set. Okay. This is most interesting and important. Now, how many possibilities are there? Instead of saying that this 1, 2, 3, how many ways can be arranged? How many ways can be arranged? You will be getting that number of that number of functions you will be getting. Therefore, this 1, 2, 3, how many ways that can be arranged is nothing but permutation. Therefore, this group is called the permutation group. So therefore, you know that 1, 2, 3 can be arranged. There are 3 letters. Therefore, 3 factorial ways we can arrange. Okay. So therefore, any set X consisting of 3 elements, we can make 3 factorial functions. Suppose X is equal to 1, 2, 3, 4. We will make 4 factorial 1, 1 onto functions. We can get it. So therefore, the permutations are 1, 2, 3. This is 1, 2, 3. Let us take this is I. Let us take this is I. Then 1, 2, 3. 2, 3, 1. This is another function. Let us take this is sigma 1. Then again 1, 2, 3. 3, 1, 2. This is nothing but sigma 2. Okay. Likewise, 1, 2, 3. I can take 1, 3, 2. 1, 3, 3. This is equal to tau 1. This is equal to all functions. I can denote like that. Again, 1, 2, 3. 3, 2, 1. This is equal to tau 2. 3, 2, 1. Okay. Again, I can write 1, 2, 3. 2, 1, 3. 1, 2, 3, 2, 1, 3. So therefore, this is equal to tau 3. So therefore, the x is equal to 1, 2, 3. I can collect all the functions, all the permutations is nothing but S3. A set consists of S3. S3 is equal to I sigma 1, sigma 2, tau 1, tau 2, tau 3. Tau 1, tau 2, tau 3. Okay. This is very important group. This group is called symmetric group. Or otherwise we can say that it is a permutation group. Otherwise we can say that it is a permutation group. Again, we can make a multiplication table for this. We can make a multiplication table for this. Okay. The product of 2 permutations, the product of 2 functions is nothing but 1 goes to 2. If you multiply with identity element, you will be getting the same element. Okay. So therefore, suppose if you multiply this and that, 1 goes to 2, 2 goes to 1, therefore 1 goes to 1. You know that. So okay. Z1 into Z2, the operations I can say that Z1 composition Z2, because it's a function. Composition Z2, the sigma 1, the composition sigma 2 is nothing but 1 goes to 2, 2 goes to 1, so therefore 1 goes to 1. 2 goes to 3, 3 goes to 2, therefore again 2. 3 goes to 1, Again 1 goes to 3. So therefore again 3. So therefore sigma 1 into sigma 2 is equal to again I. Likewise, you go to operation is here is composition. Operation is composition, because of function. So therefore composition of functions. If you multiply all those things, you will be getting a multiplication table. You will be getting a multiplication table in which you can check one by one. You can check it. What is the inverse of 5? Inverse of Z1. What is the inverse of Z2? Inverse of Z3, tau 1, tau 2, tau etc. You can find. Okay. So therefore, this is very interesting group. This is also a cyclic group. This is also a cyclic group. Okay. A subgroup. Suppose I am taking a subgroup here. Let us take a subgroup. Suppose H is equal to I sigma 1 sigma 2. Okay. Here, this is also a group because now only we have seen that sigma 1 into sigma 2 is equal to I. Sigma 1 into sigma 1, you will be getting again sigma 2 or something like that. Sigma 2 into sigma 2 is sigma 1. You can check it very well. So therefore, identity is that. Therefore, this is a subgroup. This is a subgroup, number 1. This is also a cyclic group. You can check very well that this H is cyclic also. You can check very well. Okay. Because Z1 is a generator. Z2 is also a generator. Okay. Cyclic group. The most important thing is this is not an abelian group. H is not an abelian group. This is the very good example of not H, I am saying that this S3. S3 is not an abelian group. S3 is not an abelian group. From the table, you can check it that sigma 1 into sigma 3 or something like that. You will not be both will not be equal. Both will not be equal. You can check it. So therefore, S3 is not an abelian group. Okay. So this is most important group. So this is nothing but a collection of all 1, 1 onto functions from X into itself. Number 1. Another thing is that there are a lot of things are there here. Then next one is, so S3 is the the example of non-abelian group is S3. Matrices also we can say that with respect to multiplication, non-abelian group we can say. Okay, and S3 is not an this is a subgroup and all. So every permutation we can check whether it is odd permutation or even permutation also we can check. Okay, suppose 1, 2, 3, 3, 2, 1 is there. We can check whether this permutation is even or odd. Even or odd. So 1 goes to 3. We have to write it in a cycle. 1 goes to 3. Okay, 3 goes to 1. Okay. So therefore, I can write this in a product of two cycles. Product of cycles of order 2. If it is 1, this is odd. This is odd. Okay. So this permutation is called odd permutation. This permutation is called odd permutation. So therefore, you can check it that I is even. Sigma 1. Sigma 1 is equal to what? Sigma 1 is equal to 1, 2, 3. 2, 3, 1 is sigma. So we can check it that what about this is whether it is odd or even. 1 goes to 2. 2 goes to 3. 3 goes to 1. This permutation can be expressed as a product of cycles of order 2 or 3 or something like that. Here, this can be written as a product, that is a cycle of order 3, cycle of order 3. This cycle of order 3 also can be expressed as the product of cycle of order 2. The product of cycle of order 2, that is 1, 2, that is 1, 2 and 2, 3. 1, 2 and 2, 3. That's all. If you have third order cycle, you will be getting, suppose if you have the cycle of order n, if you have the cycle of order n, then you can write the product of n minus 1 product of the two cycle product of cycle order 2. So therefore, here there are two number of cycles of order 2, product of cycle of order 2, two cycles, order 2, or otherwise we can say that two cycles. The product of the two number of two cycles, the product of two number of two cycles, therefore the product is 2, therefore the permutation is called even. The permutation is called even. I is equal to what? I is always, we can say that this is 0, order 0 we can say that. So therefore this is even permutation. Sigma 1 is even. Sigma 2 is also even. Sigma 2 is nothing but 3 to 1. This is also you can write 1 goes to 3. 1 to 3, 2, 3, 1, 3 to 1, 1 goes to 3. 3 goes to 1. Sigma 2 or something like that. 1, 2, 3. What about sigma 2? This is 1, 2, 3. This is I. 1, 2, 3. 1, 2, 3. 2, 3, 1. 2, 3, 1 is sigma 1. 3, 1, 2. 3, 1, 2 is equal to sigma 2. This is sigma 2. Sigma 2 is equal to 1 goes to 3, 3 goes to 2, 2 goes to 1. Again, I can write the product of two cycles. So therefore, 1 goes to 1, 3 and 3, 2. 1, 3, 3, 2. So this is also even. So therefore, in this S3, you can check very well that I, sigma 1, sigma 2 are all even permutations. Tau 1, tau 2, tau 3 are odd permutations. You can check tau 3 is also odd permutations. You will be getting a odd number of product of two cycles. Okay. So therefore, what I am going to say is, if you collect all odd permutations, I, sigma 1, sigma 2, if you collect all odd permutations, you will be getting a alternating group A3. This is most important. This group is called alternating group A3. So from out of S3, we can get A3. S3 consisting of 3 factorial, therefore 6 elements. So here we have only 3 elements. So therefore, this group is called alternating group. Then order of A3 is equal to 3 factorial by 2. In general, suppose Sn has n factorial, An has n factorial by 2 elements. N factorial divided by 2 elements. So therefore, from the symmetry group, we can take the alternating group. Alternating group consisting of all the even permutations. All the even permutations. Okay. So if we can take S4 consisting of, you will be getting how many? 4 factorial. Therefore, there are 24 permutations to be there. There are 24 permutations. So therefore, these are all permutations. Very important concept. Then left to coset and right coset. Okay, so this is also most important concept of subset. Let G be a group. let G be a group, H be a subset of G, H be a subset of G, right coset, let A belongs to G, the right coset HA of A is equal to, HA can be written as the set of all HA such that all H belongs to H. This is called right coset. This is called right coset. Okay. So what are the properties? My question, you can ask immediately that whether this HA is a subgroup. You can ask. Okay. If HA is a subgroup, what will happen? You have to think like that. Similarly, I can left coset I can define. I am only concentrating right coset. Similarly, you can do it. Okay. A belongs to G. H is a subgroup of G. H is a subgroup of G, not subset. Not only the subset, it also will be a subgroup. Suppose what I am going to say that HA intersection HB either is empty, HA intersection HB, that is distinct, or HA is equal to HB. Any two right cosets are distinct or either distinct or identical. That is most important. Why we have taken this left coset means, if you take one A belongs to G, you will be getting one HA. The elements of H will not be altered, the elements of HA. For example, I am telling you that, let us take a subgroup, let us take a group G is equal to 1 minus 1 I minus I. Okay. Now I am taking one subgroup H is equal to 1 comma minus 1. 1 comma minus 1. Okay. Very interesting. G be a group, H be a subgroup. Now I am going to construct a right cosets. Now I am going to construct a right cosets. For each element, 1 belongs to G, I can take H1, right coset. Right coset in the sense set of all H into A. H elements 1 minus 1, therefore 1 into 1, again 1. 1 into minus 1, again minus 1. So therefore H1 is equal to again H. Let minus 1 belongs to G. H minus 1 I am taking. HA. So again this is equal to minus 1 plus 1. Again it will be H. Let I am taking A belongs to G. A means what? I belongs to G. Then HA can be written as I comma minus I. If you multiply it, I comma minus I. Okay. Then minus I belongs to G. Then again H minus I can be written as I and minus I. You see that now I have taken all the right ideals. All the right ideals of a subgroup H. All the right ideals of the subgroup H. Understood? Now you see that H1, 1 and minus 1, 1 and minus 1. So H1 and H minus 1 both are equal. Or you consider this is distinct. So no right cosets, no pair have a common element. See that? Either identical or distinct. So no common element. Either totally identical, equal, okay, but distinct. So see that. So therefore, this G can be partitioned. This G can be partitioned. Partition is nothing but what? H1, I can write H1 and Hi. H1 and the two distinct right cosets. H1 and Hi. Okay. So therefore I can say that any two right coset of a group, of a subgroup, either identical or distinct. That is most important. Now, the intersection is empty. The union is equal to G. Union is equal to G. H1 and Hi is equal to G. Okay. Now, this G can be partitioned into two sets. Okay. Suppose here the number of elements order of H is equal to 2 here. So here order of H is equal to 2, order of H1 is also 2, order of H minus 1 is also 2, order of HA is also. So therefore there is no change in the order. Okay, understood. So therefore here H1 is equal to 2, H2 is equal to 2. Therefore this is order of H1. Order of H1 is again order of H plus order of HI is also again order of H. Order of H distinct, therefore I can take plus. This is equal to order of G. So therefore I can say that 2 times of order of H is equal to order of G. 2 times of order of H is equal to order of G. So therefore order of G divided by order of H, is equal to some number that is 2. So this implies I can say that order of H divides order of G. Okay. So this is nothing but Lagrange's theorem. Okay. So therefore here what Lagrange's theorem says, let G be a finite group. H be a subgroup of G, and let H be a subgroup of G, then order of H divides order of G. So this is most important theorem in our group theory. That theorem is called Lagrange's. So for proving this Lagrange's theorem only, we need this right cosets and left cosets. So any two right cosets are identical or distinct, either identical or distinct. Okay. So therefore I can I think I can stop with this. I think. Okay, Professor.
Okay, Professor.
Professor, shall I stop or continue?
Your option, sir.
Okay. Thank you, Professor.
Just over 5 minutes.
Okay.
Question hour.
Question. Okay, you can ask questions.
Okay.
Homomorphism also is there. There are a lot of things are there.
Sir, one more question, sir.
Tell me.
First, you can preliminary definition in